This is a simple guide to first-order linear equations from differential equations. I'll divide this video up into 4 subchapters consisting of 1. What is a first-order linear differential equation? 2. Its general form. 3. The steps to solve for a solution, given a problem. And 4. An example problem walkthrough, in which I'll choose one problem from a textbook and give a general walkthrough to it. The timestamps will be on the description below. So, what exactly is a first-order linear differential equation? Well, first, the highest-order derivative in the equation is dy dx, obviously, since it is first order, meaning there is only a single power of a derivative. There is no, for example, d squared y dx squared. It can only be to the first power. And additionally, it doesn't have to necessarily be dy dx, it could be dx dt, as long as you can generally recognize that there is in fact a derivative. Secondly, it must be linear. By that I mean there are no radicals or exponents being applied to any y terms. By y terms I mean just any dependent variable, meaning you don't take the radical of the dependent variable y, you don't square the entire derivative term, or just have any sort of funny business with the dependent variable apart from its original form. C, constant coefficients are allowed, so essentially you can have stuff in front of the dependent variable as well as its derivative, as long as it's not a function of the dependent variable, meaning you can't have like y squared times y, for instance. That breaks the rule. But however, you can have 5y or x times dy dx, since it's a function of x, the independent variable, or e to the x times dy dx, etc. And as an add-on to this, anything goes for the independent variables, meaning you can have x to the, let's say, 100th times y, and then, blah, blah, blah. I'll talk about the general form in a second. But you can do anything you want to the independent variable, as long as it's not really messing with the dependent variable. And that's pretty much it. Let's move on to the form of a first-order linear differential equation. So the general form is as follows. A sub 1 of x times dy dx plus a sub 0x times y equals b of x. So a sub 1 of x and a sub 0 of x are essentially just functions of x. It can be whatever terms you want. They can even be equal to each other, as long as there's no y involved or anything with dependent variables. So for an example I outlined here, I wrote x squared, where a sub 1 of x is x squared, times dy dx plus a sub 0 of x is equal to 5 times y equals e to the x, where e to the x is equal to b of x. In another example I wrote dy dx plus y equals 7 plus x cubed, where 1 is a sub 1 of x and 1 is also a sub 0 of x, to illustrate the fact that they can also be equal to each other and also just be 1. Lastly, 7 plus x cubed is equivalent to b of x. And also keep in mind that b of x could also just be equal to 0, in which we'd call that a homogeneous equation, in which the right-hand side is just essentially 0. So yeah, that's a general overview of how the general form is made. Now let's move on to the step-by-step instructions. Now we are on to part 3 of this video, in which we cover the steps to solve for a solution for a first-order linear differential equation. Though these steps may look a little overwhelming, don't worry, I just made sure to write as much as possible to make it very clear, but you'll eventually find these steps to be very intuitive and easy. So let's break it down. Step 1 is where we first isolate dy dx by multiplying or dividing, in which we put it into standard form, as you can see here by the arrow, dy dx plus p of x times y equals q of x. So all we have to do is, let's say for example there's a 7 in front. You divide this entire equation by 7, and by doing that you manage to isolate dy dx. That is the most important rule. You don't really care what happens to p of x or q of x, as long as you have dy dx by itself. Next, you have to recognize what p of x is. It's essentially just the coefficient in front of y. It also includes the negative sign, so if instead you had dy dx minus p of x times y, you have to absorb that negative into the p of x equation, so you have to always have it be in plus form. And after that, you integrate p of x, or whatever is the coefficient of y. And why do we integrate it? Well, it's to find the integrating factor, mu of x, where mu of x equals e to the integral p of x dx, or with respect to whatever the dependent variable of the equation is. Why do we need to do that? Well, if we already found p of x by integrating it, all we have to do is plug it in to the exponent of e, and then we're already halfway done the equation. This is pretty simple stuff, if you think about it. So once we found mu of x, or I of x depending on what the textbook calls it, you multiply the entire equation by mu of x, including the dy dx term, everything by mu of x. To clarify, you multiply everything by mu of x like that. By doing that, you will set up a future product rule, and by that I mean on the left hand side you'll be able to simplify it in the term of dy dx times mu of x times y equals, whatever happened to the q of x term. So it will always be in this format, dy dx, or the derivative of the dependent variable with respect to the independent variable of the integrating factor times y, and it will always take that form, so you don't even need to worry about that. And afterwards, you integrate both sides to isolate for the y, since if you take the integral of dy dx, that will give you the just inner terms of that. And after you do that, just isolate y by typically dividing by mu of x. And after that, you have the entire equation in terms of y. And if you have any constant c, if you're given an initial value problem or initial conditions, all you do is plug it in, the plus c, and you'll get your fully formed solution. Now let's put these steps to work. So for the example problem, I chose this problem in which dy dx minus y over x equals x times e to the power of x, and we are given an initial value y of 1 equals e minus 1. All that the initial value does is turn it from a family of solutions to a single solution, since you're given a single point. So now let's go through this step by step. So first, we can see that there is no coefficient in front of the dy dx, meaning that it is already in standard form. Now we have to recognize what exactly is p of x. Well, as you can see here, p of x, I'm just looking at this term right here, p of x equals negative 1 over x, since that is equivalent to negative y over x. So the coefficient is negative 1 over x times y. So let's rewrite that, p of x equals negative 1 over x. So we have now successfully found p of x, the coefficient of y. Now, like I said before, we integrate that. So the integral of p of x dx equals negative, I'm bringing out the negative sign, integral 1 over x dx. So this is a fairly simple integral. As we all know, the integral of 1 over x is ln x, and all we do is throw in the negative sign in front of it. So negative ln absolute value of x, and we do not add the plus c yet. We leave that to the end of the equation when we fully form it. So this is now what the integral of p of x dx equals. So next step, what is mu of x? Well, mu of x, the integrating factor, equals e to the integral p of x dx. Since we already found the integral of p of x dx, all we do is plug in this, e to the power of negative ln x. However, we can't simplify this down, since we know we can simplify in general, since there's an e and ln, inverse functions. We can't actually simplify this yet, since there's a negative in front of the ln. That turns it from an inverse to a non-inverse function. So to put e and ln right next to each other, we can use a simple logarithmic property in which you bring the coefficient of whatever's in front of the ln term as the power of whatever's within the ln term. By that I mean e to the ln x to the power of minus 1. All we did was move the minus 1 coefficient as the exponent of the inner term x. And now we can finally simplify this, meaning mu of x, the integrating factor, equals 1 over x, or x to the power of negative 1. Now that we have mu of x, all we do is multiply everything in this equation here by mu of x. So 1 over x times dy dx minus 1 over x squared, because negative 1 over x times 1 over x is just negative 1 over x squared, times y equals, if we multiply x times e to the power of x times 1 over x, the 1 over x and x cancel, so that all that equals is e to the power of x. So that step is now done. Now let's simplify the left-hand side as a form of product rule, in which we already said dy dx of mu of x, 1 over x, times y, equals whatever's on the right-hand side, e to the power of x. We can double check if this is correct by looking at, on the left-hand side, is this in fact the derivative of 1 over x times y? Well, we can see the derivative of 1 over x is negative 1 over x squared, we see that here, times y, that's correct, plus 1 over x times the derivative of y, so this is in fact correct. So now that we know that's proper, we integrate both sides to get rid of the dy dx and isolate the y term. And we are doing both of these with respect to the independent variable x. This becomes 1 over x, whatever's on the inside term, times y, equals the integral of e to the power of x dx is simply e to the power of x. And now you can add the plus c, since we're almost done forming our final equation. And now we can either a, isolate for y and then plug in the initial value, or we can just immediately plug in the initial value since c is already by itself and we don't want to multiply by x and then plug in the values because that might be a little risky. So I think now is a safe time to plug in the y of 1 equals e minus 1 to find c. Meaning the initial point is 1 comma e minus 1. So let's keep that in mind. So we can see here a 1 over x, that becomes 1 over 1, times y, where y is e minus 1. So we kind of don't even need the 1 over 1, so we'll simplify that in a sec, equals e to the power of x, which is 1, so e, plus c, which is what we're trying to find. Let's rewrite that, e minus 1 equals e plus c. We know that the e's will cancel, since if you move one to the other side it will be e minus e, which equals 0, and that leaves us with the c value equal to negative 1. So now that we found that, we can finally plug that back in. So 1 over x times y equals e to the power of x minus 1, which was previously the value of c. So now we can do the final step, in which we isolate for y, which is a solution to this equation. So let's multiply by x, which would cancel the 1 over x, turning it to 1. It becomes y equals x times e to the x, all we're doing is multiplying that, minus x, which is negative 1 times x. And that is in fact our solution to this equation. See, if they didn't give us the y of 1 equals e minus 1, then it would just remain as plus c, and you don't need the minus x here. If you would like more examples relating to this topic, I have a playlist link below in which I do quite a few examples relating to this topic. I'm sure you'll find at least one example that covers what you're looking for. If you have any questions, please leave in the comments below, and good luck.